make sure that this setup is most easily available to make that transfer easiest, as much of the previous work doesn't have this possible. Previous work was only done in simulation, allowing the robots to play the piano with hands that can phase through each other, fingers that overlap, something that could never be reproducible in a real-world system. So as you can see, this is our physical environment setup. We have 3 Ned2 robots. Now, Ned2 robots are relatively low-cost robots, allowing our project to be accessible not only to us, but then to others to then take this, build upon it, and replicate our project as well. And as you can see, our robots are strategically placed around the piano. We have 2 on the top and 1 on the bottom. This allows them to have the most range of keys that they can reach without colliding with one another. Since there are many hardware limitations to our robots in terms of speed, and also, as you can tell, we have a single gripper, so it can play only 1 key per arm, 2 at most if they're a specific distance away. So the main part is making sure that we can have all 3 of these robots working together to play a music piece. So, how do you get from music all the way to our robots playing this on the piano? So you could start off with sheet music or actual human playing and convert those into a MIDI file. Now, a MIDI file is computer-readable music. This conversion can be done with a variety of apps that can take direct sheet music and convert them into these files, or you can also have specific instruments that are enabled that they can convert the playing on the instrument to this MIDI file themselves. We then take those files into our system and put them into our simulation. We do this by taking all the information that we need and slicing up this file to basically take what key should we play at what time, which is the major information that the robots are going to need. We then put that into our simulation environment, and this is the environment which will do all of the actual learning, because as the robots are trying to figure out how do I press these specific keys at those specific times, we don't want them to collide with one another as they're exploding, hit the piano, break the system. That would be very costly and a lot more time consuming to do this on the real system. So that takes place in our simulation environment. Then once that simulation environment outputs a desirable piece showing, hey, it's playing the piano, it's not.
For each of those, and we store them into arrays for easy access. After that, we utilize the collected drum positions to play simple songs. So, for example, we pulled Mary Had a Little Lamb, a MIDI file of that from the internet, incorporated that into our code, and then using the drum positions that we collected, the robots played the songs. After that, we set up the simulation environment using MuJoCo. MuJoCo is a physics software that we use. So for each of for the piano and the robots, we had to put each of those modules in there separately. And as you can see, it is exactly like the robot setup for easy transfer later. And we use this for our testing so that we use that for testing so our robots don't accidentally break, as there are limitations with velocity and movement, or we don't want to damage any of them by colliding them. After that, we generate the MIDI files to serve as training data set for the reinforcement learning. So with our computer, we use the software to play simple songs or pieces of songs or just notes on a piano, and then recorded those and converted those into MIDI files using the software.
As Joe had mentioned, the initial real-world testing involved hard-coding the robots to play the piano piece, so providing the robots with the actual positions and locations to go to. So the first video shows a single arm playing Mary Had a Little Lamb. And then the following video shows multiple robots playing Mary Had a Little Lamb at the same time. So this utilizes multi-threading, which is multiple robots playing at the same time and being able to work collaboratively. And then the final one is multiple robots playing the piano at the same time within the same octave. So following the initial setup, we then set up the simulation environment, and this simulation environment had to be slowed down tremendously due to the hardware capabilities of the robots. The robots could only move at a certain speed, but as you can see, the simulation mimics the real world setup exactly. There are some small, minor differences. such as you can see in the simulation, the robots are seen to be floating. Compared to the real-world setup, they're actually on the tables. But this allows for, after setting up the initial testing phase in the simulation environment, we were then able to move to reinforcement learning, where the robots can actually train and press the correct keys without being provided the locations of those specific keys. Okay, so the reinforcement learning algorithm that we chose to use is called Soft Actor Critic. The way Soft Actor Critic works is it uses two different neural networks that work together to develop the best policy. So the actor network is what controls the actions that the robot takes in simulation, and then those actions change the state of the environment. The state of the environment is described by a reward function that the critic network takes to output a value that the actor uses to determine what the next action that it's going to take. And this is the cycle that continues as we train our simulation until we are getting the results that we would like. So the reward function that the critic uses is defined by things that we want to encourage the robot to do and things that we want to discourage the robot from doing. So the things that we want to encourage the robot to do are getting close to the key, so we have a distance reward that is proportional to how close the end effector has gotten to the key that needs to be played at that time. We also have a position reward for if the robots actually hit the key at the correct time, because we especially want to encourage that behavior. Our penalties are velocity and collision. So our velocity penalty is discouraging the simulated robots from moving too quickly because, as Nadine mentioned, there is a velocity limit on the actual physical robots, so we don't want the robots to try and damage themselves and move too quickly if this is transferred to the real world. We also have a bigger collision penalty discouraging the robots from hitting each other or hitting a part of the keyboard that they are not supposed to hit. We obviously want to discourage them from damaging each other or damaging the piano.
So let's see this. So let's see our build simulated environment in action with moving components and audio. So here we have a robotic arm playing Mary Had a Little Lamb. This performance is driven by real-world priors, which are recorded joint angles and positions from the initial testing phase. We chose this approach to base our learning off of using real-world data in hopes of reducing the learning time. And the goal is to make it more likely that what happens in sim can be transferred to reality. If you notice, the arms tend to fling themselves at the target keys without caring how they get there. This is because we only use the positions for the priors, so it doesn't matter how they get there, it just kind of teleports when it needs to be. To clarify, this is before the velocity and collision penalties that Sana mentioned prior, and this is a starting point for the RL to learn off of, provide structure, providing realistic positions, and reduce randomness and exploration. It starts, the learning then will tend to take over with all the physics constraints, and then the robot arms will then choose to avoid collisions, choose which arm to play what, and do so efficiently and smoother. Since the starting behaviors are based off of real life behaviors, this will make it the goal of the final policy to be easily transferable from sim to real hardware.
So our consideration towards future work for this project, transfer learning, essentially moving from simulation to the real world, we were not able to get this process because even with a stable policy in the simulation environment, the policy and the model of the learning was so that there's a lot of exploration, and so the policy is exploring and trying to improve itself, whereas in the real world we wouldn't want it to fling itself around more wildly or do anything that is outside of the scope of the physical constraints of the real world. And so we were not able to transfer from this portion, from the simulation to the real world. However, our consideration towards it was using what we found was the digital twin. The MuJoCo digital twin essentially does the opposite. Instead of going from simulation to the real world, it goes from the real world to the simulation. And we use that to verify the model as accurately as possible to the real world. So as you can see in the video, we have someone with a hand just moving the robots into positions and then mapping where it would be inside the simulation. And then as you can see, it is relatively pretty accurate. It's not perfectly accurate. There are potential errors, which means that there might be potential like filtering and curving that would need to be done from the model to go from simulation to the real world, but that is our consideration towards the future. This is the task allocation for all the members of our project. Thank you.
Have you considered, like, in your reinforcement learning process, that how could you sense